Okay, so continuing on. So the approach that I initially took here is for each planet to have its own script. So I've got a bunch of planets. They each have their own script. We're going to use the find by tag, find game objects with tag planet, use that to calculate the force that it feels due to all of the other planets, and then move itself. And we're going to use this Verlet method. So the code has initial position, mass, and this is the non-central code. It has all the initial conditions. It has an array for all of the other planets that it's going to find. And it has slots for force and acceleration, position, velocity, and so forth. So in start, we find all the other game objects. We go through and get their masses. We need that in the calculation. And we catch the position of our planet. And then I'm going to use a coroutine with Verlet just so that I can insert weights if I need to. And so Verlet's an I enumerator where I calculate force over mass. Force over mass is just minus g, the mass of the other one, divided by r cubed times the vector radius between them. Notice there's a trap here so that I'm not calculating the r cubed between myself and myself, because that would be a divide by 0, and this returns the total force. And then here's the Verlets where I update position, update the velocity with that acceleration, recalculate the acceleration, and update it again. This is an alternate form of Verlets that uses 2 half steps. And then I'm updating the position and waiting for an end of frame. So that's one approach to this, and that works just fine. Here's a 2-body problem going around each other, calculating the force due to the other planet, and so forth. Now, alternatively, we could use a central manager, a game object that was responsible for knowing where all the planets are and calculating the forces between them and moving them. And one of the reasons for doing this is the fact that Unity is not actually threaded at the object level. Each of these different scripts on each of the different planets running concurrently are not running on separate threads. That would be nice if they were. It would be a powerful parallel programming tool. Another thing that we can do with a central manager that we couldn't with the non-central scripts is calculate the total energy of the system. The total energy is a diagnostic in the sense that the total energy is conserved in an n-body problem. And consequently, if in our numerical methods we find that the energy is drifting, then there's something wrong, and the numerical method is not using a small enough time step or some other problem. Another thing that we can do with the central manager is handle collisions. And I wanted to do this. I wanted planets to bump into each other, stick together and form a larger mass, and then continue on with their procedure. And so a central manager is, I'm going to have a distinct planet that I call the sun. It's not actually treated any differently from the others, except that I want to be able to make its mass different than the others. And here I've got an array for planets, energy, angular momentum. Planar has to do with the initial conditions. Starting these things off is a very delicate procedure in terms of getting a bunch of objects that either don't all collapse into each other or don't all blow apart to infinity. And so I'm doing this with a sphere, and planar is how much I'm flattening that sphere. You'll see examples of this in a little while. Softening is kind of a cheat to deal with planets that come too close to each other. So the various arrays to hold everything on start, we set up the sun, a special object that we're going to have, usually yellow, giving it particular coordinates. And then we go through and set up all the planets, picking them out of an array of possible planets that we'll use, giving them a random location, setting that planarness to flatten out the sphere, and then some magic here to calculate initial velocities that will produce realistic results without blowing up. When all this is initialized, we're going to start coroutine Verlet, and notice that my start here is an I enumerator. So I'm able to yield on the start coroutine Verlet, which means it will block there until Verlet's done. And then here's my collision tester that's going to decide what happens when things collide. And I'm going to calculate the energy, which I can do at each time step, as well as the angular momentum. In a collision situation, I'm eliminating objects periodically. And so periodically I need to renumber them, which I do just by basically going through and throwing out any that have been turned to null. Right here, if it's not null, I re-add it back into the arrays. This could be an expensive step. Collision tester checks the distance between objects, and if they're too close together, it's going to instantiate a little explosion. And then we need to go through figuring out what happens to them after they collide. First, I want them to grow. I want them to be bigger, so I need a new size. And two, I want to conserve the momentum. Collisions are not energy conserving, but they are momentum conserving. So my new mass is going to be m1 plus m2, and by volume is radius cubed. So my new scale is the new mass raised to the 1/3. Conservation of momentum says that the original momentum, m1v1 plus m2v2, has to be equal to the new momentum, m1 plus m2 times the new velocity. And so I can easily calculate a new velocity, which remember is a direction vector. And so this is going to go off in some other direction with a new speed. And here's the code just to do that. The new velocity, the new mass, and its new size, and then I'll destroy the other object so that it's gone. One other little trick is a function that puts things in the center of mass system. This ensures that the system doesn't drift off screen. A lot of the particles will go off screen, but they do that going away from the center of mass. So this is just a trick to keep the largest majority of them on the screen as they blow up. Verlet in this vector version is just kind of a vector version of what we did for the individual particles. We have vectors of accelerations for the force on mass I. We have vectors of positions that are updated. We have, again, another vector of accelerations, and again, another vector of velocities that are updated. This is the vector version of Verlet's. And because unity is three-dimensional, all of these are three vectors, and we don't have to deal with X, Y, and Z components. Force over mass is more or less identical. It loops over all of the objects, checking to make sure that I'm not checking the force due to myself, or that the object has not been destroyed in a collision. And here's that GMI over R cubed times radius, calculating the force. Calculate momentum, just does the cross product between x and velocity, position and velocity. And energy sums up the kinetic energy, 1/2 mv squared, and the potential energy, this nested loop where we calculate the potential between each object I and every other one. And we're careful not to count them twice here. So let me show you some examples now with this. Well, let me stop sharing here, and I'll come back in and show you examples in just a moment. I'll see you in class. Bye.